Have you ever wondered how Netflix, Amazon, or Jio Hotstar handle millions of users at the same time? Answer is in load balancers. They keep traffic smooth, prevent crashes, and make sure your requests reach the right place. Let's break it down in the simplest way possible. In this video, we'll explore the different types of load balancers and how they compare within the OSI model. We'll also break down the various algorithms used in load balancing and compare load balancer offerings from different cloud providers. Imagine you have a website with thousands of users. Behind the scenes, a load balancer is managing the traffic, distributing requests to multiple servers for smooth performance. But suddenly, one of the servers goes down. What happens next? Does the system crash? Do users face downtime? No. The load balancer detects the failure and automatically reroutes traffic to the remaining healthy servers. The system stays up and users experience no disruption. Now, the two active servers share the extra load, ensuring the website keeps running. This is called automatic failover, a key feature that keeps modern applications reliable. Now, let's discuss OSI model. Imagine you're at a pizza restaurant. You walk in and a waiter greets you.
Hello, sir. What would you like to have, a classic margherita or a spicy pepperoni?
This waiter isn't just randomly handing out food, he's understanding your request and making sure you get exactly what you want. Now, compare that to a simple food counter where pizzas are made and handed out, no questions asked. Just first come, first served. This is exactly how Layer 7 and Layer 4 load balancers work. Let's break it down. First up, Layer 4 load balancer. This one works at the transport layer, meaning it deals with IP addresses and port numbers. But it doesn't care about the content of your request. Think of it like a traffic cop at an intersection. If too many cars are heading to one road, the cop redirects them to another available road. But the cop doesn't check if you're a bus, a bike, or a truck, just where you're going. In the tech world, this means a Layer 4 load balancer will route requests based on IP addresses and ports, but it won't check if the request is for a login page, a video stream, or an image. Now, let's level up. Meet the Layer 7 load balancer, the smart waiter of the internet. This load balancer works at the application layer, which means it actually looks inside the request before deciding where to send it. Let's go back to our pizza restaurant analogy. If you order a vegetarian pizza, the waiter makes sure it's prepared at the right station. If you order extra cheese, the waiter directs it to the right chef who specializes in custom orders. In tech terms, a Layer 7 load balancer can route traffic based on URLs. Example, login goes to one server, videos goes to another. On the other hand, cookies and sessions to keep users on the same server for personalized experience. And also, headers and API requests to optimize backend efficiency. Now that we've understood Layer 4 and Layer 7 load balancers, let's dive deeper. What really happens inside a load balancer? How does it decide which server should handle your request? Well, that's where load balancing algorithms come in. First, let's dive into round-robin algorithm. Round-robin sequentially distributes incoming requests across multiple servers in a cyclic manner. Each request is assigned to the next server in line, ensuring an even distribution of traffic. Once the last server in the pool receives a request, the cycle restarts from the first server. This method is simple, stateless, and effective for environments where all servers have similar processing capacity. However, it does not consider real-time server load, which can lead to inefficiencies if some servers are busier than others. Variants like weighted round-robin address this by assigning different priorities to servers based on their capacity. Now that we've covered round robin, let's move on to another widely used algorithm, least connections. Unlike round robin, which distributes requests sequentially, least connections dynamically assigns traffic to the server with the fewest active connections at any given moment. This approach is particularly effective when requests have varying processing times, ensuring that no single server becomes a bottleneck. For instance, if one server is handling 36 connections while another is overloaded with 100 plus connections, the next incoming request will be directed to the less busy server. By constantly monitoring active connections, least connections helps balance traffic more efficiently, improving overall performance and response times. Now that we understand this, let's move to another important algorithm. Unlike the previous algorithms, IP hashing assigns requests based on the client's IP address. Let's break it down. It applies a hashing function to the client's IP and maps it to a specific server. This means that requests from the same client always go to the same backend server, ensuring session persistence. IP hashing is particularly useful when handling stateful applications, where maintaining user sessions on the same server is crucial, such as in online banking or e-commerce platforms. However, one limitation of IP hashing is uneven traffic distribution if certain IPs send significantly more requests than others. Now that we understand IP hashing, you can explore another powerful techniques like weighted round robin and least response time algorithms in the notebook. Let's see very quick glimpse of both the algorithms. Bonus content different cloud providers comparison is present in the notebook. You can see the link in the description. Thank you for watching. Please like, share and subscribe. If you are having any doubts, you can catch me in the LinkedIn. Added the LinkedIn profile in the description.